as we start this part of the third part of the chapter, dealing with cardiac output, make sure that you understand the 4 definitions that are there right underneath Roman numeral 3, cardiac output, in your notes. So again, cardiac output is the volume of blood pumped by a ventricle in each minute, and our default will be the left ventricle, again because that's the one that pumps out to the organs, in particular the brain. Can we calculate cardiac output? Yes, we can. If we can measure stroke volume, which is the volume of blood ejected by a ventricle with 1 beat, so milliliters per beat, and heart rate, we know what that is, beats per minute. So we can actually calculate this. Stroke volume times heart rate equals cardiac output. So take a look at this and answer these thinking questions. You have an answer for me yet? Well, let's take a look then. So if heart rate increases, what's going to happen to cardiac output? This relationship between what is on the right side of the formula and what is on the left is a direct or proportionate relationship. In other words, if heart rate increases, cardiac output will increase. If stroke volume decreases, cardiac output is going to decrease. Okay, so they are proportionate. So we know how to measure heart rate. We can just put our finger on pulse and count the beats per minute. But how are we going to figure out what stroke volume is? Well, nowadays there are tables that are have been researched for the difference between males and females, body size, etc. But if we can, using imagery, if we can estimate the volume of blood at the end of diastole, that would be when the ventricle is most full, and then we can estimate the volume of blood at the end of systole, which is at the end of ventricular ejection. That's going to give us stroke volume. So we could say here, as I have in your notes, stroke volume is end diastolic volume minus end systolic volume. The difference between the two when the ventricle is the most full and when it is the most empty. Here is a really good flow chart that shows what and how cardiac output is influenced by. So changes in heart rate, that is primarily driven by the autorhythmic cells, and changes in stroke volume, which is influenced by the force of contraction. So we'll take a look at this in more detail in class also. This is a really good illustration of the change in the pacemaker potential of the SA node under normal circumstances, and if we were to add even more acetylcholine to the SA node. So under drastic parasympathetic stimulation, the bottom of the wave would be below -60. It actually would be hyperpolarized, which means it's going to take longer to reach threshold. Now, the fire part is going to be the same, but the drift is taking longer, and that means that the entire rate is slowed down. And that's why the parasympathetic effect of acetylcholine results in a decrease in heart rate. This slide shows the effect of sympathetic stimulation. Again, here is the normal rate of pacemaker depolarization compared to when we apply norepinephrine or epinephrine to the SA node. So if we apply norepi or epi to the SA node, the membrane doesn't reach -60. It stops slightly above it. And that means the time it takes for the drift portion is shorter. It reaches threshold more quickly. And again, the fire phase is the same, but the drift takes less time, and therefore the rate of depolarization is increased. And so when we look at epi and norepi, we know the result is an increase in heart rate. I've added this slide in to show you that our catecholamines, epinephrine and norepinephrine, don't just increase the rate of cardiac contraction, it also increases the force of cardiac contraction. And the biggest reason for this is we talked in A&PII about the beta-1 adrenergic receptors on the heart. They are not only on the SA node, the AV node, they are everywhere. Everywhere, including on the contractile cells. And for this reason, epi and norepi, we said, increases heart rate, but it also will increase force of contraction. Now, these concepts are going to show up in our cardiac physiology lab, and you'll be able to actually see these heart rate changes, which we would call chronotropic changes, and force of contraction changes, which we call inotropic changes. We're going to see that in lab, so we'll study this more later. As future health practitioners, you may have come across ionic imbalances in patients' bodies. And you may see hyperkalemia, hypokalemia, hypercalcemia, and hypocalcemia. And we are going to, especially in lab, take a look at why those ionic fluctuations cause these various changes. So we have a couple of functions of physics, really, that influence cardiac output. Let's take a look at preload first. Preload is the volume of blood that goes into the ventricles. If you add volume to that chamber, you will be stretching the walls of that chamber. When you stretch the walls of the chamber, you stretch those cardiac muscle cells, and that triggers a myogenic response. It is reflexive. Myogenic, that means that as you stretch the muscle cells, it generates more force of contraction. So preload means that there will be an increase in diastolic volume, and that is going to result in an increase in force of contraction, which will increase cardiac output. Now, let's look at afterload in a second. Afterload can also influence cardiac output. Basically, afterload is a function of there being resistance to flow coming out of, in this case, the left ventricle. So if, for example, the aorta is experiencing arteriosclerosis, hardening of the arteries, there may be less room for blood to flow through that blood vessel. That means in order to overcome that resistance, the ventricle has to contract with more force. So in order to maintain cardiac output in this case, there must be an increase in force of contraction to overcome the afterload.